Hi, in this video, we are going to cover Chapter 5, Newton's Laws of Motion. We will first talk about forces, and then we will go over the first, second, and third law of motion. And then finally, we will talk about weights and normal forces. Okay, let's start. So Chapter 4 was about kinematics. It's basically the study of motion. So this is an example to a kinematics formula where you can calculate the position if you are given initial position, time, initial velocity, and acceleration. So this is basically kinematics. But this chapter is about dynamics. And dynamics is basically, it's the study of forces. So we will learn about the famous formula F equals ma. Now, when we did kinematics, we did not really question where this acceleration came from. But in this chapter, we will learn that the acceleration is actually, it occurs whenever there is force, net force. So what is force? The force is push or pull. It's a vector. It has a magnitude and direction. And there's a reminder here. So mass is, so we talked about force, acceleration, and what about mass? So mass is the quantity of matter in an object. Also, mass is the measure of how hard it is to change an object's velocity. So if the object is light for a given force, you can change its velocity easily. But if it's a heavy object with higher mass, then it will be harder for that object to change its velocity. So you can think of mass then as the measure of how hard it is to change an object's velocity. Okay, force is a vector. Now we have a concept here. It's called net force. It is the vectorial sum of all forces on a given object. So let me give you an example. Let's say if you have this box and if you have two forces like this, one of them is to the left, 19 Newton. The other is 20 Newton to the right. So if you do the summation of vectorial summation of these forces, what you end up with is 1 Newton to the left. So this is the net force. So the net force is basically, again, the vectorial sum of all forces on a given object. So you don't just, add all the forces on different objects. You may have different objects at other positions. You may have an object here, an object at other positions, and there may be forces, but net force is about always consider one object at a time. So what about the second situation? Here, there's 20 Newton to the left and 20 Newtons to the right. The net force is, of course, in this situation, it's 0. The total is 0. So, but net force 0 doesn't mean there's no forces on the object. So net force equals 0 basically means there may be forces on the object, but they cancel each other. So there are forces on the object, but since they cancel each other, the net force becomes 0. So in the following slides, we will be interested in the net force, not the forces, not the individual forces on a body. What about the third case? Now we have two forces on the horizontal, 20, 20 in each side, and then there is this 3 Newtons in the negative y direction. So these 20s, they cancel each other, and what's left is 3 Newtons in the down direction. Again, this is the net force, which is 3 Newtons in this case. Okay, so if the net force on an object is 0, so if net force is 0, if this is the case, then the object's velocity will not change. So it doesn't say, so be careful, it doesn't say the object's velocity is 0. It just says the object's velocity will not change. That means there is no acceleration. So there is a connection between net force being 0 and acceleration being 0. And in the following slides, you will see the formula, which is actually F net equals ma. So there's a note again, which I actually mentioned before. 0 net force doesn't mean there is no force on the object. There may be forces on a box pushing it and a friction force in the opposite direction. So maybe there's a box here, maybe someone is pushing it this way, and maybe also there is some friction force. So if these cancel each other exactly, if these two forces are exactly equal, then we can say the net force will be 0. Okay, so what happens if F net is 0? So there are different situations, 1, 2, and 3. So one is the object will not speed up or slow down. Okay, if F net is 0, the object will not speed up or slow down. The other thing is the object's velocity direction will not change. So, for example, if the object is going in the positive x direction, if there's no net force, it will not, it will not turn. It cannot. It will always go in the positive x direction with the same magnitude. So remember, velocity is a vector. So it has the magnitude, which we call speed, and it also has a direction. So when we say velocity will not change if F net is 0, we mean both the speed and the direction will not change. And also, if the object is still means not moving, it will not start moving. So if you have in a box again, let's say one person is pushing it to the right with, say, 5 newtons, the other person is pushing it with 5 newtons. If the initial velocity is 0, this box will just stay here. It will be still. It will not start moving. Okay, so these lead to the concept of inertia. It's related to the word inactive. So inertia is the resistance of an object to any change in its velocity. Both, we mean, when we talk about velocity, we mean both the magnitude and direction. So basically, the objects have inertia, which means if there's no force present, net force, then we say that they will resist to change. They will not change their speed, their velocity. And if there is some force, they will present some resistance to change in their velocity. So that resistance, you can only win against that resistance, which is inertia, if you have a force. So only net force can change the velocity of the object. Okay, let's start with Newton's first law of motion. So this is the first one. What does it say? It says an object at rest means velocity is 0, remains at rest as long as no net force acts on it. So you have a box. If the initial velocity is 0, it will be always 0 if there's no net force, if net force is 0. Again, net force 0 doesn't mean there are no forces. Maybe someone is pulling it and also pushing it with exactly the same forces, F. Well, right now there are forces, but the net force is 0. So in that case, again, because no net force acts on it, it will not move. Okay, what about the situation where the object is moving? An object moving with constant velocity, that means there's no acceleration. It's already moving with constant velocity. Okay, it's moving. So it continues to move with the same speed and in the same direction as long as no net force acts on it. Okay, this may be a little bit counterintuitive because in real life, you see if an object is sliding and you know that it's going to stop at some point. But that's because there is usually, and it's actually almost always, friction between the object and the ground. Or if it's in the air, there's going to be some air resistance. So that's why it's actually stopping. But if you think about the object, if you ignore the resistance and the friction and the air resistance, the object actually moves forever in the same direction with the same speed. This would happen if, for an object in the sky, and if that object is not pulled strongly by any other object around, like a sun, earth, or if there's no net gravitational force on the object, so that object, we can assume that that object will move the same velocity in the same direction forever. So basically, the first law of motion is saying that if the object has zero velocity, it will always have zero velocity if the net force is zero. Or if it has some speed, or let's say velocity, its velocity also will not change if there's no net force. So from that, you can infer that the only change in velocity, the only way that the velocity can change is that when there's a net force. The definition of net force, we talked about this. It's basically summation of all the forces, but this is a vector summation because there are vector signs on it. So F1 plus F2, so you sum up all the forces on a given object. You don't add forces on different objects. Always, you focus on one object at a time. If you add them up, then if you get zero, that means F net is zero, so that object, so in that case, Newton's first law will be valid. So zero net force may mean no forces at all. That's one possibility. Or the second possibility is there may be forces acting on an object, but they cancel out when vectorially added up. So we talked about these two possibilities. Okay, what about the second law? So Newton's second law tells us an object may have several forces acting on it, but the acceleration occurs due to the net force. So if the net force, so you basically add them up, and if it's not zero, then it's equal to m times acceleration. So this is the famous formula from Newton. In fact, this is also valid if F net is zero. So if this is zero, then we get acceleration zero. Again, zero acceleration doesn't mean zero velocity. Zero acceleration means the velocity will not change. If there is initially zero velocity, okay, it's gonna be zero velocity forever. If the object has already some velocity, it will not change. It will continue to be the same velocity. So what changes the velocity? It could be slowing down, it could be speeding up, or it could be changing the direction of velocity. What you need is acceleration, right? And for acceleration to be non-zero, you need non-zero net force. The unit of force is Newton, which is equal to kilogram meter per second squared. Why is it so? Now look at this formula. So mass is kilogram. We are using SI units. And acceleration, if you remember, acceleration is meter divided by second squared. So you can use this one for force, or you can basically say just Newton. So Newton is just, it's not a fundamental unit, it's basically just a shortcut for this whole thing. Okay, we can do one observation. If F net is zero, then acceleration is zero, because we look at the formula. And that means velocity won't change in that case, if F net is zero. So if you remember this kinematics formula, so velocity at any time depends on velocity, initial velocity plus acceleration times t. If acceleration is zero, then this term is gone. So what's left is only this part. So if acceleration is zero, that means whatever the initial velocity is, the final velocity or velocity at any time, it will be exactly the same. Because if there's no acceleration, positive or negative, then it will, the initial velocity will always be equal to the initial velocity. Okay, let's do one numerical example now. So in this problem, we have a box of 2 kilograms, and there's one force to the left and one force at 60 degrees with the horizontal line, and it's 40 newtons. This object is already moving with 5 meters per second. So this is the initial velocity. In this problem, the right direction is taken to be positive x direction. Okay, so the first part is find net force in the x direction. So we will always divide the forces in horizontal and vertical. So let's do the first one. The first part. So F net in the x direction. So I have to find the components, right? So this vector F2 has 2 components. One of them is this one, y component, and the x component is this one. In this problem, there's really no question about the y direction, so I will not really calculate the y component, but I will calculate the x component. So this angle, so this is close to the angle, so I have to use, close cosine. So it's going to be 40 times cosine 60 degrees. And cosine 60, if you look at here, it's 0.5. So this is going to be 20 newtons. Okay, what is F net? Let's find F net in x direction. So I'm going to write 20 with positive sign. See, because 20 is to the right. And to the right is defined to be positive. So it's going to be 20. And this 14 newtons, it's in the negative direction. So I will write it as negative 14. So this is going to be 6 newtons. So F net in the x direction is 6 newtons. Okay, now let's move to the second part. What is acceleration in the x direction? Of course, I have to use F net equals ma for the x component. So F net is 6, m is 2, ax. So from here, what we find is acceleration in the x direction is 3 meters per second squared. Okay, what about the third part? Now the third part is not dealing with, we're not going to be dealing with forces. So this part is actually kinematics. So we will just use the kinematics equation, which, if you remember, is initial velocity plus acceleration plus times t. So the initial velocity is given in the problem. It's positive 5. And acceleration is 3. We just calculated. And the question is, what is the speed or velocity at 3 seconds? So we're going to multiply by 3. So this is 9. So it's 14 meters per second. So the first 2 parts was dynamics because we dealt with forces. And then the third part was kinematics, which goes back to chapter 4. Okay, let's talk about free body diagrams. A free body diagram shows every force acting on an object. So if you look at this figure here, so a person is pushing the chair, right? So to be able to do calculations, I will show all the forces on the chair first, which is here. This is called a free body diagram. This is free body diagram. Why is it free body? It's free body because there are many objects here. There's even a person that pushes the chair. But if we are interested in the chair, we just isolate it. We just isolate it and then draw the forces on it. So this is important. Isolate the object of interest. In this case, it's the chair. Sketch the forces on the chair, not the person, because we're interested in the chair. Choose a coordinate system and find x component and y components of F net. And then finally, you can calculate the accelerations in any direction, x or y. Okay, what are the forces on the chair? First of all, the easiest one is the gravity, right? This chair is on the earth, so the earth is pulling it down. The other one is the chair is not in air, it's on the ground, right? If it's on the ground is actually pushing it up. This is called normal force. Now, if you are standing right now, the ground is actually pushing your feet up. If you are sitting, the chair is pushing you up. That's the normal force. So think about this. What is the reason that you put your feet up, maybe on a chair, or on the bed? So you don't like your feet on the ground whole day. Why? Because whole day you are either walking, sitting, or standing. Your feet are touching on the ground, right? So all the time the ground is actually pushing your feet from the ground, right? So you all the time during the day you feel a push under your feet. So that is, to relieve that push, when you come home you put your feet up in the air, or sometimes on a sofa, so that you can feel the relief. So this is the normal force. So whenever there's ground, so that is pushing it up on that object. So okay, what are other forces? So the person is pushing it down kind of in this direction. So I'm going to call this F person. There's one more force. If you push an object in any direction, there will be some friction force in the opposite direction. And that friction force is, again, it's because of the ground and the object. So I'm going to show it in this direction. So that's the friction force. Okay, now I can move all the forces together to a point. So the normal force is up, weight is down. The force, the external force on the chair coming from the person, is kind of in this direction. Okay, and there is also friction to the left. So I can move all of them to this point. Can I move the vectors? Yes. As long as you don't change their direction, you are free to move the vectors to other places. Okay, so that's what free body diagram is. Here is another example of a free body diagram. If you are holding a book like this, what are the forces on the book? Not on your hand. I know you feel some weight, some normal force. Not the weight, but the normal force from the book. But we are not, let's focus on the book now. What are the forces? Well, just like usual, because that's on the earth is pulling it down. If this was the only force, then the book would fall down, right? But it's not falling down, so there should be another force that keeps it in balance here, and that force is the normal force, and that normal force is coming from the hand. So this is from the hand, normal force from the hand on the book. See, all the forces, these two forces, are the forces on the book, not on the hand. And for free body diagram, you don't have to really draw the book. You can do it like this. Just put a point and show all the forces on that point. So this is the normal force. You can show it as N, and this is the weight. Okay, let's move to Newton's third law of motion. It's the action-reaction pairs. If object one, let's say we have two objects. If object one exerts a force F on object two, in this case, let's say object one is the person, object two is the fridge. So the object one is exerting force F on the fridge. Then object two, which is the fridge, exerts a force, negative F, which is here, on object one, which is the person. So basically it says if there is a force, then there is also another force which is exactly in the opposite direction, but with the same magnitude. Think about a falling apple or the apple on the tree. Doesn't matter. So the earth is pulling the apple down, right? It's either falling or it's still on the branch. In either case, the earth is pulling the apple down. Okay, does the apple pulls the earth up? The answer is yes. The apple is also pulling the earth up, and with the same force in terms of magnitude, it's the same, except it's in the opposite directions. So basically, Newton's third law, if there's a force, there is definitely another force which is the same in magnitude, but in the opposite direction. That's always the case. Okay, now I have a couple of warnings here. The first one is this figure with the fridge and the person. This figure shows one force pair. This force and this force. They are coming in pairs. So, but this figure is only showing these forces. There are other forces, such as the friction force pair. It's not shown here. So, and one acting on the ground. So, one acting on the fridge and one acting on the ground. But these are not shown here. So, on the fridge, basically, if you push the fridge to the right direction, there will be a friction force on the fridge in the left direction, right? Okay, what about this? Does the fridge also exert a friction force? Or let me put it this way, is there also friction force that the ground itself feels? Yes. The friction force that the ground feels is actually to the right. Of course, the ground is, I mean, the earth is huge, or the building or the room that you are in with the fridge, you are not going to be able to move it, but still there is that friction force. So in this case, the pairs are still here, the friction forces, but one of them is in the opposite direction. Okay, the other warning is, do not think these forces will cancel each other and the fridge will not move. No. Don't ever think, this is very important, don't ever think this force and this force will cancel each other. No, they won't. Think one object at a time. For example, for the fridge, you have to consider the forces acting on the fridge only, not the forces acting on the person. The reason that these forces, this force pair, do not cancel each other because they are acting on different bodies. So this force on the right, it's acting on the fridge. But this force in the negative direction, it's acting on the person. So whenever we apply F net equals ma, we always look at for the forces on one object, either the person or the fridge. So remember, free body diagram is done only one object at a time. So let's do it for the fridge first. So the fridge has the weight, so WF. It has a normal force. Why? Because it's on the ground. If it was falling, if it was in the air, there wouldn't be any normal force. But because it's on the ground, there is normal force. What about the weight? If it's falling down, if an apple, if it's falling down, let's say, does it have weight? Yes. In fact, weight for an apple falling down will be the only force on an apple, because there wouldn't be any normal force, well, because it's not on the ground. Okay, what are the other forces on the fridge? Well, there's friction to the left. Why? Because the person is pushing it to the right. So the friction force is always opposite to the movement or the possibility of the movement. And there's also the force that's exerted by the person on the fridge. So let me move all the forces here on this dot. The normal force is up, the weight is down, the friction is to the left, and the person, the external force on the fridge due to the person, is to the right. This is the free body diagram for the fridge. If this force, the external force due to the person, is greater than the friction force, then F net will be non-zero, and the object will accelerate towards right. So if you can win against the friction force, then of course you can push the fridge to the right. Okay, let's do the free body diagram now for the person. Okay, if you do free body diagram for the person, now let's isolate the person. Now, this force, I'm not really interested in on this force because this force is not on the person. It's applied by the person on the fridge. But now we are going to do free body diagram of the person. So we will only look at the forces, find the forces exerted on the person. So the first force is that I want to point out is the force because of the fridge, right? So the fridge is applying force to prove it to you. What you can do is, for example, you can push the ball and then see if you are really feeling anything on your hand, or push any object, or try to push a sharp object. What happens? Pushing a sharp object is the same as pushing the sharp object into your hand. It's the same thing, right? Either you push the sharp object with your hand, or keep your hand at the same position and push the sharp object into your hand. You will exactly feel the same thing. Because if you push something, that object is pushing you back, your hand, with exactly the same force, except in opposite direction. So if you are pushing the fridge with, let's say, 30 Newton, the fridge will push you back with 30 Newtons. The other forces are the same: the weight of the person, the normal force is up, and now the friction is in the right direction. Why? Because the fridge is pushing you to the left. Remember, the friction should be in the right direction. If this is a little bit confusing, think about this situation. If the friction is not to the right, then let's say there's no friction, what would happen? If there's really no friction here, what will happen is, if you push the fridge, this person will actually slide to the left. Imagine there's some oil or some really slippery object, material, some fluid. If there's no friction, what would happen is you will actually move to the left. So remember, the friction, you would move. If friction is 0, you would move to the left. So remember, the friction is in the opposite direction to the movement. So the friction force on the person is to the right. Okay, now let's go back to the apple. And I am pretty sure that you had the question that how can the apple pull the earth with the same force? So let's start with this. In nature, this is actually a third law, Newton's third law of motion. In nature, there is no single force. So you cannot really find any force like this. There should be another force. If this is, let's say, F, there should be somewhere another force exactly in the opposite direction. So forces always come in pairs. So if the earth pulls an apple down, an apple on a tree pulls the earth up with the same strength. The apple here on the tree, or the apple that's falling, they are always pulling the earth with the same force in the up direction. Now, I know you have this question in your mind, which is, why do we always see apples falling down, but not the earth falling up towards the apple? So the hint is actually, so again, this equation, right, F equals ma. So what I'm telling you is that the forces are the same. The force on the earth and the force on the apple due to gravitational attraction is actually the same. But then why is earth and apple move differently? Let's answer this question. The answer is the earth and the apple pull each other with the same strength. So the earth and the apple are pulled towards each other, but the earth's acceleration is so small to notice, as its mass is so large in comparison to an apple. You can see it here. So the formula is F equals ma, right? So you're going to have two of them. So the forces are the same, okay? So we have the Earth mass and the Earth's acceleration. We have the apple's mass and the apple's acceleration. Now I'm going to write it for the acceleration. The forces are the same. So if you write the acceleration, force divided by m Earth, and for the apple, again, so these are the same numbers, okay? Same forces. And you can calculate it from Newton's gravitational attraction formula, which we will see it later in the other chapters. So if you look at here, for the Earth's acceleration, you are dividing F by some huge number, and then you will get really, really small number for Earth's acceleration, right? For the apple, you have the same force, but you are dividing it with small number, so you will get a large acceleration. So this acceleration is small, in fact, extremely small number, and this acceleration of the apple is large. So acceleration of the apple is so large than the Earth's acceleration, we don't really notice the Earth is moving. So think about this thing. So the apple is falling down, so the Earth is huge. So, but they have the same forces, F, okay? But their accelerations are different. Let's say if this apple falls down for 1 meter, and the Earth, its acceleration is so small, maybe it moves, I don't know, maybe 1 nanometers, or maybe 10 to the negative 20 meters. You can actually calculate it. So that number is extremely small. It's extremely small distance that we don't really notice as the Earth is moving. But in principle, yes, the Earth is also falling towards the apple. So the lesson here is equal forces on different objects don't mean the acceleration of each object will be the same. Even though we have equal forces on each object, the apple and the Earth, but their accelerations are different because their masses are different. Okay, so now we're going to do this exercise where there are two canoes. The person on canoe 1, this person here, he is pushing canoe 2 with force F2, which is given to be 46 newtons. So the masses of the canoes are different. Of course, if this person is pushing the canoe 2 to the right, what will happen is this canoe will move to the left and canoe 2 will move to the right. So because the masses are different, of course, the accelerations will be different. So first, we are going to find the accelerations. And then in the second part, we will find the separation between the canoes, because maybe this canoe will move here, the other one maybe will move here. So we will find this separation between the canoes at time equals 1.2 seconds. So because we are dealing with the forces, let's do the free body diagram for both canoes. Now each canoe has the weight and the normal force. Why there is a normal force? Well, it's because they are in water. Water is buoyant, so there's a buoyant force. It's not necessarily a hard surface, but still it exerts force on the canoes. But in the y direction, they are not really moving. This canoe is not sinking, it's not going up. So I will just ignore the y motion because, well, there's no motion in the y direction. So we will only focus on the motion on x. So the second canoe feels the force F2. It's actually the force that this person is exerting on the canoe. So this F2 is actually coming from this person. And the canoe 2 is actually, if this person is pushing the canoe this way, the canoe will push that person with the opposite and the opposite force with the exact same magnitude, right? So F1 and F2 will be actually the same thing. But F1 is the reactionary force from the canoe 2 on the person's hand. Okay, so how are we going to find the accelerations? Well, we will write F equals, we will write F net equals ma for canoe 1 and canoe 2. So let's do it for canoe 2. So F net on the second canoe, will be, it's given in the here in the problem, it's 46 newtons. And what is the canoe? What is the mass of the second canoe? It's 250. And the acceleration, I have to write A2 because I'm solving this question for canoe 2. So from here, you can find A2 to be 46 divided by 250. Okay, what about the acceleration of the first canoe? So first of all, you have to use now Newton's third law, which is, the action-reaction pairs. If this person is pushing canoe 2 with 46 newtons, that means this canoe will push the person's hand, and consequently the canoe 1 with the same force in the opposite direction. So F1 should also be 46 newtons. So this is going to be 46 again. Now the difference is the mass of the first canoe, which is 150 times A1. So the acceleration will be 46 divided by 150. Now A1 is larger. Why? Because we are dividing the same number, which is 46, by a smaller number. So A1 will be larger than A2. Okay, so now in the second part, we will find a separation between the canoes. So I have to calculate. Now I'm going to do kinematics. I have to calculate how much these two canoes, so this is the 0 point, will move from this 0 point. By the way, A1 is because the canoe 1 is moving in the negative direction. I have to write a negative sign here. And in fact, the force is also negative. So for the first canoe, the position of the first canoe will be the initial position, which is 0. Initial velocity of the canoe will be 0. So I can write 1 here, plus 1/2 A1 t squared. So initial velocity of the canoe is 0, initial position is 0, because we can take these points of the canoes, we can say they are initially at x equals 0. So from here, x1 would be 1/2 A1, which is negative 46, divided by 150 times t squared, so it's going to be 1.2 squared. So there's going to be some negative number here. And for xt, the same thing. Now instead, we will use A2. So x2 will be 1/2. A2 is 46 divided by 250 times, again, 1.2 squared. And this is going to be some positive number. Let's look at the solution. So if you do this division, A2 becomes 0.18. The acceleration of the first canoe becomes negative 0.31. So you calculate how much their final positions. The final position of x2 is positive number because this canoe will come maybe here. So that's a positive number. And the first canoe, its final position is negative, so it's somewhere here, negative 0.22. This point is 0.13. So what is the separation? The separation is this. How do you find it? Well, you basically subtract the numbers and take the absolute value. You can do x2 minus x1, take the absolute, or you can do x1 minus x2 and take the absolute. Because you are taking the absolute value at the end, it doesn't matter which one you use. And the answer is 0.35 meters. Now, one thing that you have to notice here is, even though the forces are the same, just like the apple and the earth problem, their accelerations are different. See, one of them is 0.18, the other is 0.31 meter per second squared. And because the accelerations are different, each canoe, and why are they different? Because the masses are different. And now, because the accelerations are different, each canoe moves at a different rate, right? So the second one has more acceleration, so the second one moves actually more in that given time. Okay, let's move on. So there are two kinds of forces. One of them is the contact forces, like you push the fridge and the fridge pushes you back. So contact means touching, you really touch the object. And there are also non-contact forces. And the example is, so contact forces, example for that is I just mentioned here. But there's warning here. Note that there are other forces on the person. So there's a friction on the person, there's weight, other forces. And also on the fridge, such as friction, gravity, which are not shown here. So we are just showing these two forces only in this figure. But of course, there are other forces as well. Now, the other option is the non-contact forces. Non-contact means not touching. And it's that example is the gravity, right? So if you have a plane or an apple, and there's the earth, these objects will have forces, gravitational forces. So gravity is an example. They will pull each other without touching each other. And here's the warning that I did in the previous slides. Action-reaction pairs, like this force and this force, or this gravitational pull on the plane and the same force on the earth, they do not cancel each other, as they act on different bodies. So these two forces do not cancel each other because one of them is on the earth, the other one is on the plane. So you should always focus on one body at a time when using a free body diagram. Okay, here's a question. If the force by the person on the fridge is equal and opposite to the reactionary force exerted by the fridge on the person, how come the fridge moves to the right but the person don't move to the left? The answer is, think of each body separately. Again, we are on the same subject. The person exerts force F on the fridge, which is this one. And if this force is greater than the friction force that acts on the fridge, what is the friction force that's acting on the fridge? It should be to the left because the person is pushing it to the right. This is the friction on the fridge. If this force is greater than the friction force that acts on the fridge will move towards right. If this force is greater than the friction, then the fridge will move to the right. As for the person, now let's think about the person. If the force on the person due to the fridge does not overcome the friction force acting on the person. Now we are talking about the person, so we have to think about the forces on the person. So the fridge is pushing to the left, and the friction on the person is to the right. Friction on the person. So if the force on the person due to the fridge does not overcome the friction force acting on the person, the person will not move towards left. So because this friction force, if it's greater than the force due to the fridge, then the person will not really move to the left. But if this force from the fridge on the person is greater than the friction, let's say there is some oily fluid on the ground, so it's slippery on the ground, then in that case, yes, this person would move to the left. Okay, here's an exercise. Assume no friction in this problem, so there's no friction between the blocks or on the ground. The first part is find acceleration of the blocks. So, and in the second part, find the magnitude of the contact forces F1 and F2. So let's look at the forces first. So let me do the blocks here again. There's one block, there is another block. Okay, so there is this external force, 20 newtons. Now, it first says find the acceleration of the blocks. So let's think about the blocks as one object. Okay, so think about them as one object because they will accelerate together, right? The blocks cannot have different accelerations in this case, they will, because they are moving together. So the blocks definitely have the normal force and the weight, but I will not really, write them down because we are interested in the movement in the horizontal. So in that case, 20 newtons is the only force on the blocks, right? So F net equals M, in this case, total M times acceleration. So F net is 20. What is the total mass? It's 15 kilograms times A. In this case, A is 20 divided by 15, which is 4 divided by 3 meter per second squared. So this is the acceleration of the blocks together. Now, you may ask, okay, how is this large block moving? There's really, is there any force on it? Well, if this block is accelerating, yes, it is. There should be some force. Well, that force is coming from the block 1. So what's happening is when you push this little block, it uses some of the force from here to accelerate itself, and it transfers some of the forces to the large block so that the large block also accelerates at the same rate. So now if you look at let's focus on for the second part. So we can do the free body diagrams for the first block and the second block. So now we are going to isolate them. So this one is the 5 kilogram one. So what are the forces on this one? I'm just going to put down only the forces on the x direction, x-axis. So there is this force, 20 newtons. Okay. Now, because it touches the large block, because it's pushing the large one, right? If it pushes the large one will push back. Again, Newton's third law, action and reaction. So this force will feel that, so we call this F2. It will feel this F2 force. Okay, let's do the large one. This is the large block. This is 10 kilograms. Now, what are the forces on this large block? Well, look at the figure here. The only force that comes from, 20 is not really acting on this large block, right? 20 newtons, it's acting on the small one. The only force that acts on the large block is F1. So F1 is the force exerted by small block on the large block. Okay, just because it's here written like F1 is shown within block 2, it doesn't mean that this is acting on block 2. This is actually from block 2 acting on block 1. So, and F1 is the only force on the large block, that's it. So if you are going to write down F equals MA, let's write it down for the small block. So let's choose right direction as the positive direction. So any force to the right, I will take them to be positive. So 20, I will take it in positive sign. So 20. F2 is in the negative direction, so I write its magnitude as F2. Okay, equals m. M is 5 times acceleration. That acceleration, I don't know. So it will be acceleration of block 2. The small one is block 2. Okay, let's write the same equation for this one. So the only force acting on this one is F1, its magnitude, equals m is, the mass is 10, and its acceleration is, because this is called block 1, it will be block 1. Okay, now we do know something, which is these blocks move together, right? So they actually have the same acceleration, and that acceleration we already calculated. That acceleration is actually here, even though we thought them as one block, but it doesn't matter. I mean, if as a whole, if this object accelerates with 4 divided by 3 meter per second squared, that also means this object acceleration, its acceleration is 4 divided by 3, and the acceleration of this object is 4 divided by 3. So then this is 4 divided by 3, and this is 4 divided by 3 as well. Let's look at the solution. So in the first part, we used the total mass, so M total. M total was 15. And so we did 20 divided by 15. So we found the acceleration to be 1.33 meter per second squared. Now in the second part, which is about finding these forces, the contact forces between the blocks. Let's move to the other page. So we did write F1 for the large box, because if you remember, for the large box, the only force, 10 kilogram, the only force that acted on it is the force coming from the small blocks, which is F1. So mass is 10 for the large block. The acceleration is, we just calculated in the previous slide, 1.3 meter per second. And if you calculate the force, you find F1 to be 13.3 newtons. Now, what about F2? Now, F1 and F2, they should be equal, right? In vectorially, they are equal in magnitude and in opposite directions. So let's focus on the small block now. The forces acting on the small block are 20 and F2. And if you remember, I did write 20 minus F2. So this is the small blocks, 5. So there's 20 pushing to the right. And there is the reactionary force from the large block, which is F2. Now the mass of the small box here, which is 5 kilogram. And the acceleration is, again, the same acceleration that we found in the first part. So 133, there should be 3 here. And if you calculate, you find the force F2 to be 13.3 newtons. So from this equation, we find, so basically 20 minus F2 equals this multiplication, which is this number. Now solve for F2, which you find 13.3. Now, what was F1? Look at F1 here. And look at F2. They are actually, the magnitudes are exactly the same. And that's what we expect, right? They are the forces, action-reaction forces in the opposite directions, but the magnitudes are exactly the same. Okay, so there's one note here. We found F1 and F2 are equal and opposite. If you write F1 and F2 in vector form, write it as F2 vector equals negative F1 vector, because the directions are opposite and it brings a negative sign. But when we write the magnitudes, and since the magnitudes are by definition positive, we write it as F1 magnitude equals F2 magnitude. And if you remember, the absolute value sign of a vector means its magnitude. And it could be in the negative direction, the vector, but again, the magnitude is a positive number. Okay, now let's do this exercise. The two people here, 1, 2, they are pulling the sled in different directions. So, but with the same angle, 35 degrees each, with the same magnitudes of forces, but of course in different directions. Now there's also friction force, which is 55 newtons. The question is, find the acceleration of this acceleration A of the child. Now in this problem, because these two people, they pull the sled to the left, I will choose left direction to be positive. Okay, so it's up to you to choose which direction to be positive. It's, choosing a coordinate system is completely arbitrary. It's up to you. So for this coordinate system, now what are the forces? To be able to find the acceleration, you have to find F net. So to be able to find F net, you have to show all the forces. So I'm going to put a point here. Now, what are the forces on this object? Child and the sled. So I will think of them as, one object because they are moving together. So one force is the friction force, which is 57 newtons. The other forces, one of them is in this direction. The other one is in that direction. So now these will have some some components, right? So how do you calculate those components? This is 55. The other one is also 55. Okay. So now there is this y component. If this is 35 degrees, how do you calculate it? Well, this will be 55 times sine 35. And there's going to be x component, and it will be 55 times cosine 35. Now, this one also has this component, which is exactly, again, because the angle is the same, 35 degrees, 55 times cosine 35, and also this component, 55 times sine 35. Now, these are all the forces that you have to consider. Now, if you want, you can rewrite it as, let's just write the components now, sine 35. So what I'm trying to do is write the components only in exactly x direction or y direction. So 55 sine 35. So here, these are the same, right? So I will just multiply it by 2. So it's going to be 2 times 55 times cosine 35. And there is also the friction force in that direction. Now, you can look at these forces and you can easily say there is not going to be any acceleration in the y direction because, this force and this force, they will cancel each other exactly. So the acceleration in the y direction will be 0. Now, what about the x direction? So now let's write down the forces. So we will write down this F net equals MAX. And this M will be total M. So what are the net forces? Let me write this first. It's to the left, but I will write it with positive sign because in this problem I chose positive direction to be left direction to be positive. So plus 2 times 55 cosine 35. Now 57, it's to the right direction, but it's negative direction for this problem, for the coordinate system that I chose. So it comes with a negative sign. Now, what is the mass? The mass is the child plus sled. So it's going to be 19 plus 3.7. And now the acceleration. So basically calculate the cosine of 35, do the multiplication, and then finally divides both sides with this 22.7. And that will give you the acceleration of the child and the sled, which will be in the left direction, which is shown here. So if you do the calculation, it turns out that 33.2 divided by the total mass gives you the acceleration in the x direction. And it's plus 1.5 meter per second squared. We find plus because the acceleration is to the left, and you can see it from the figure, and left direction is actually the positive direction in this problem. Okay, so now we will talk about weight. So mass is the amount of matter, for example, so that means like how many carbon, oxygen, and hydrogen atoms in your body. It will not change if you go to the moon, if you go to the sky, right? It's going to be always the same amount. So that's mass, and it's measured in kilograms. Kilograms is SI units, but if you are in the United States, they use pounds. If you're in the UK, sometimes they use, stones or different units. That's fine. But it's basically the amount of matter. But the weight, on the other hand, is a force. So weight is a force because now you remember probably weight is calculated by m times g. G is the gravity of Earth if the object is close to the Earth. This is actually from the formula F equals ma, right? Gravity of the Earth is an acceleration, mass, and weight is a force. And force is measured in units of Newton. So now, because it depends on gravitational acceleration, the weight changes if you go to the moon because the gravitational acceleration g is different on the moon. So, but of course, in daily life, people, we use these interchangeably, or sometimes you confuse them. For example, you shouldn't confuse them in physics. The data usage is different. So, for example, we say my weight is 50 kilogram in daily life, right? Everybody says that. But actually 50 kilogram is the mass here. Remember, kilogram is the unit of mass. So what we have to say is actually my mass is 50 kilogram. Okay, what about the weight? If your mass is 50 kilogram, what would be your weight? Your weight would be 50 times 9.8, which is the gravity of the Earth. It will be approximately 490 newtons. Okay, now let's move to normal forces. The normal force is the force exerted by a surface on an object. Okay, so the normal force is by a surface on an object. So note that the weight is the gravitational force acting on the object. Weight is not the force acting on the surface. The force acting on the surface is the negative of normal force. Now look at this soup can. So what it says here is weight is not the force acting on the surface. So when you see it like this, we show the weight force. It looks like it's acting on the surface, but no, we are actually showing, we have the soda can. It's just weight. Weight is basically the force by the earth on the object because of the gravity. So it has nothing to do with the surface. Even if the soda can is, let's say you threw it up, it's not on the ground, there's no surface, even then there is weight. So don't, just because it's shown like this, it doesn't mean the weight is the force on the surface. No, the weight is the force due to the earth on the object. Now you may ask, okay, so the object is, so what are the forces on the soup can? Well, there is the weight, and in this case it's on the table. There is going to be some normal force in this direction. Now if you ask, what is the force acting on the surface? Or, you know, it could be a surface, or it could be your hand, right? You could ask, okay, now forget about this, forget about the soup can. Now let's think about my hand. What is the force on my hand? Because I feel some force when I carry this soup can, right? Now that force is, if my hand or the surface is pushing the soup can up with the normal force, then the force on my hand, let's say on my hand, is then negative n. That's what it says here. Or the surface, on the surface, the force will be opposite of this one. So let's just think about the surface. What is this? What is the force on the surface? Due to the soup can, it will be negative normal force. Okay, so in the left figure, if the soup can is stationary, it's not really moving up or down, then the acceleration in the y direction is 0. So that makes sense. It's just sitting there, it's not moving anywhere. So if you write down F net equals, so let's write it down, F net equals m acceleration in the y direction. So this is 0. That means F net is 0 in the y direction, is 0. Okay, so F net is 0. What are the forces? Let's write down the forces. There is a force. Here's the free body diagram. If you choose up direction to be positive, so the normal force will come with positive sign, and the weight comes with negative sign. So this is the F net. And if it's 0, then what you find is normal force equals to weight. Okay, in this case, the normal force and the weight force, it turned out to be the same numerically in terms of their magnitudes. They are the same, but it doesn't have to be like that, and you will see an example now. So that's why the warning was there. The normal force is not necessarily the weight force. They are different things. But if the acceleration in this case, the acceleration in the y direction, if it's 0, turns out that the normal force is equal to weight. But you will see a case where that's not the case, which is in the right figure. Let's say someone is pulling the luggage in this direction with some angle. Okay, so there's this external force. So if you want to show the forces like this, so there's this external force, there's this weight, and there's this normal force because it's on the ground. Now, if you look at the moment on the x, what are the forces on the x? Well, the forces, there's only actually one force on the x-axis, if this is theta. So this component will be F times cosine theta, which is here. That's the only force on the luggage, right, in this case. And m times acceleration in x direction. So I can calculate the acceleration in x direction from this formula. Now let's think about the y direction. So in the y direction, it doesn't accelerate, right? The luggage doesn't go into the ground. It doesn't really go up, jump up. So the acceleration in the y direction is 0. So now I will write down f net y component equals ma, because acceleration a is 0, so it will f net will be just 0. F net in the y direction. So now let me write down the forces. So in the up direction, there is this force N, comes with positive sign. There is the component of this F in the up direction. So it's F, I'm going to call it Fy. This should be actually F net Y. So Fy is the component of this external force in the up direction. And if you look at the other force, weight is down. So it comes with negative sign. So let me write it again here. F net in the y direction. So because now I'm interested in the y component of all the forces, so I will write only the forces which has y component. So one of them is the normal force. The other one is the y component of the external pulling force. And the other one is the weight, but weight comes with negative sign because it's in the down direction. Now, because this is not really accelerating this object up or down, ma part, because a is 0, this will be 0. So from here, if you put these two on the other side of the equation, what you find is normal force equals weight minus y component of the external force. Now, in this case, is normal force smaller or greater than weight? Let's think about this. Say if weight is, let's say, 100 newtons, if Fy is, let's say, 20, then normal force becomes 80. So the normal force is actually smaller than the weight in this case, right? So the normal force is smaller than weight. So here, normal force is smaller than weight. But here, turns out normal force is equal to weight. So the lesson here is normal force is not always equal to weight, but there are cases where it can be equal to the weight. Okay, here is another example. So in principle, the normal force can be equal to, greater than, or less than the weight. So let's look at this example. So in the previous one, there was a luggage where there was a force that was pulling it up, which gave us a normal force that is smaller than weight. But in this case, let's think about free body diagram. Okay, so what we have is we have the weight, we have the normal force. Why is it up? Because it's on the surface, it should be up. Okay, now these two kids, they are pushing the ice block down. So this one is pushing it this way, and the other one is also pushing it this way. So these have components in down direction, right? So this is F1y, and this one is F2y. So there are also these forces. I'm going to write them as like this, F2y and F1y. Okay, now if I write F net equals, in the y direction, equals MAY. Now this block is not moving up or down, it's already on the table. So this is 0, right? So this is 0. So let me write down the forces now. So it's going to be N plus N minus weight minus F2y minus F1y. And because acceleration is 0, I will equate them to 0. Now from here, pull all the forces except normal force on the other side. So normal force becomes weight plus F2y plus F1y. So if you look at here now, the normal force, you can see that the normal force is now actually greater than the weight. So the lesson is normal force may be equal to, greater than, or less than the weight. So it just depends on the problem. But in principle, you have to keep this in mind. Normal force is the force from the ground on the object or from the surface on the object, but the weight is the force from the earth on the object. So they are in principle very different forces. Okay, they are not action-reaction pairs. They are very different forces, but depending on the case, depending on the problem, they may be equal, they may be greater or less than each other, but when they are equal, don't think that they are action-reaction pairs. They are still not same forces. They are different forces. So what is the other pair of this weight, you may ask? So think about this block, this ice block. Who is pulling it down? Well, the earth is pulling it down, right? So there's the earth here. It's pulling it down. Now, this block is also pulling the earth up. So this in the negative W with the same force, except it's in the opposite directions. So these are the action-reaction pairs, not weight and normal force. What about the reaction, the other pair of the normal force? Well, the normal force is the force on the ice block due to the table. So if this is the table, say this is the table, and this is the block here. So the normal force on the block is because of the table is pushing it up. Now, what is the pair, other pair of this force? Well, it's on the table, because the object is pulling it down. So these two forces are not related to weight. They're happening because of push, and that push is related to also electromagnetic or electric forces. When you try to push something, why do you feel it's hard? Because or right now you are sitting on a table, on a chair, right? What keeps you on the chair is the chair is pushing you. Why? Because you have some atoms, and the chair has some atoms, and those atoms, they have electrons around, and those electrons, because they are negatively charged and they have the same charge, the electrons on your body and the electrons on the chair, they actually push each other, right? So, and because of that push, there is that force. So if you look at this part really closely, what happens is this block has the atoms, and those atoms, they have electrons around. So this is the block. And the table also has atoms, and they also have electrons. Now, because those electrons has the same charge, which is negative. Now, if you try to get the negative charges together, they will actually push each other, right? So these electrons are pushing it up, and that's what we call normal force. And these electrons are pushing the electrons of the table. Of course, those electrons are pushing the atoms and all that. So the table feels that negative normal force. So as you can see, that normal force has nothing to do with gravity or weight. It's just the electrical push because of the electrons in the matter. But of course, the normal force and the weight, they show up in the same equation, F equals ma. So at the end of the calculations, you find some relation between the normal force, weight, and other forces in the system. So the normal force is always perpendicular to the surface, because the norma, it actually means in Latin, Carpenter's squared. So this is the Carpenter's squared. Carpenters use this to get, perpendicular corners or other things, or to check if something is perpendicular. So normal means perpendicular, actually, or upright. So if the surface is like this, then the normal force is not up, but in this direction. So in this exercise, we have a boy on the sled. So the total mass is given to be 40 kilograms, and the angle is given to be 30 degrees. So this angle is 30 degrees. The question is asking, what is the acceleration of this boy and the sled system? Now, in this problem, again, we will assume there is no friction. So let's think about the forces on the object. So this is the boy and the sled, this point. Now, the weight is down, always. And the normal force is not up now because the surface is, it's with some angle, right? So the normal force is in this direction. Okay, so for this problem, you can choose any coordinate system. For example, you can choose this coordinate system, but it will be easier if you choose this one. So that's what I'm going to do. So in this case, normal force is in the y direction, but the weight, it's not exactly in x and y direction, so I have to calculate its components. So the weight has, so let me draw, so this is y axis, this is y, and this one is the x-axis. Okay, so you have to find the components of weight. So this component will be weight times. So let's find the angle. If this angle is 30 degrees, now let's extend this. So this part is like 90 degrees. Okay, so if this is 30 degrees, then, or this is also 90 degrees, then this becomes 60 degrees. Now you can look at this triangle now. If this is 60 degrees, this is 90 degrees, then this angle here becomes 30 degrees. So this angle is 30 degrees. If this is 30 degrees, then here we will use cosine, and here we will use sine. So this is going to be weight times sine 30 degrees, and this is going to be weight times cosine 30 degrees. Okay, now I can get rid of this weight because I already got the components. Okay, so in y direction, I have the normal force and the y component of the weight, which is weight times cosine 30 degrees. By the way, weight is 40 kilograms times 9.8 newtons. But I'm not really interested in the motion in y because the boy is moving in the x direction. He's not moving up or down. So I'm not going to write down any equation for the forces on y, but I will write down the equation for the forces on x direction. Now in this problem, because it says there's no friction, so I will not add any friction here. So it turns out that in the x direction, the only force is weight times sine 30. So if you want to find the acceleration, write down F net, x component, is m times a in the x direction. So F net is, so weight, which is 40 times 9.8, this is g, and then sine 30 degrees equals, mass is, the total mass is given already as 40 times ax, and from here, if you divide both sides with 40, which you find ax is, so it's approximately half of 9.8, so it'll be 4.9 meter per second squared. So this is the answer. This is the acceleration of the boy down in the x direction. Okay, that's end of chapter 5.